Hi everyone, my name is Kwan. I will introduce and show you the Deutsch-Jozsa algorithm. What is Deutsch-Jozsa algorithm? Which is one of the earliest quantum algorithms. It shows us the power of quantum computing. It solves whether a given binary function is a constant function or an equilibrium function. Because the classical algorithm needs to evaluate the function multiple times to determine whether it is a constant or an equilibrium. For example, if the input function n is very large, it is necessary to perform two n⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ Deutsch-Jozsa algorithm takes advantage of quantum parallelism and quantum principles such as superposition and entanglement to solve this problem with just one query. Now, in the designing the Deutsch-Jozsa quantum circuit, we start with 2 qubits and 2 classical bits for the measurement. Initially, the qubit is in the 0,0 state. We want to put the qubit in a superposition state that can represent all possible input combinations at the same time. To achieve this, I apply the Hadamard gate to both qubits. The Hadamard gate takes the qubit out of its initial state 0 and puts it in an equal superposition of 0 and 1. This puts both qubits into a superposition state, creating an equal superposition of all input states. This means that the qubit is in the states 0, 0, 0, 0, 1, 1, 0, and 1, 1 at the same time. Now let me show you the formula. The oracle is a unitary operation that marks certain states by flipping the sign of their amplitude. This is where the function fx that we need to evaluate is implemented. If fx is constant, all terms will either be left unchanged or flipped. If fx is balanced, half of the terms will have their signs flipped. So I used a CNOT gate to simulate a balanced oracle. A CNOT gate is a controlled flip gate, where the first qubit is a control bit and the second qubit is the target bit. When the control bit is 1, the target bit is flipped. This allows me to have it generate interference pattern needed to distinguish between a balanced function and a constant function. After applying the oracle, we again apply the Hadamard gate to the 2 qubits. The purpose of this step is to use quantum interference to amplify the probability of certain outcomes while cancelling out others, thus making a decision based on whether the function is a constant or an equilibrium. Finally, if the function is constant, the Hadamard transformation will cause the final state of the qubit to always be 0, 0, indicating constructive interference. If the function is equilibrium, the state will be a superposition of the other states, which means that the 0, 0 state has destructive interference. We can see the result through the image in the output state section below. The output is shown as 1 plus 0 and 0 plus 0. This shows that only the first state 0, 0, 0 in the qubit state has a probability amplitude that is not 0, and its value is 1. The probability amplitudes of the other 3 states 0, 1, 1, 0, and 1, 1 all 0. This means that no matter how many times the circuit is measured, the final measurement result is always 0, 0, which indicates that the function being tested is a constant function because in the Deutsch-Jozsa algorithm, when the measurement result is 0, 0, 0, 0, it means that the output of the function is the same for all inputs. Also, the state vector diagram and Q-sphere diagram can also show the state of the quantum state. In the state vector diagram, the final probability amplitude has a value only at the 0, 0 position and the value is 1. This shows that the final state is the 0, 0, 0, that is, both qubits are measured as 0. This is a clear sign that the function is a constant function. The Q-sphere diagram only shows a blue dot, which means that the entire system is in state, and the final result is the same. We can see the result. By running the code, we can see that the Hadamard gate is applied when the qubits are initialized, putting them in a superposition state. In the states of the two qubits after this step, the oracle is then implemented as a CN-OT gate, with the control qubit being Q0 and the target qubit being Q1. This is an equilibrium oracle because it flips part of the input state to a different output state. This means that the output state is half 0 and half 1. The Hadamard gate is then applied again, and the function is finally balanced because the qubit states interfere with each other, eliminating some states and converting the superposition state to the standard ground state. At the end, the expected value of CZ is measured, and the result range is between -1, 1. Based on the expected value, the probability of the states 0, 0 and 1, 1 is calculated to be 0 and 0. Finally, a histogram of the probability distribution is obtained, which is all concentrated on the states of 0 and 0, and finally confirms that the tested function is a constant function. Results on constant and equilibrium oracles in the Deutsch-Jozsa algorithm. The goal is to determine whether a function is constant or equilibrium. Constant oracle always returns the same output 0 or 1, regardless of the input. When applied to a quantum circuit after measurement, the output always shows that all qubits are in the state 0 and 0. This indicates that the output of the function does not depend on the input and is a constant function. An equilibrium oracle produces an evenly distributed output of 0 and 1 for different inputs. One can see the state after applying the Deutsch-Jozsa circuit. We observe different results such as 0, 1 or 1, 0. This shows that the output of the function depends on the input and its equilibrium. As for how to tell whether the oracle is constant or balanced, after applying the oracle, the final Hadamard gate converts the superposition state into a form that can clearly distinguish between constant and balanced functions, which say if the function is constant, the quantum state collapses to 0, 0, 0, indicating that all inputs produce the same output. In this case, all qubits are in the ground state. If the function is balanced, quantum interference ensures that the measured output is not 0, 0, 0. This means that the function being evaluated produces different results for different inputs. In summary, if the final state of the measurement is 0 for all qubits, then the function is constant, otherwise it is in equilibrium. As in the end, I would like to say that the Deutsch-Jozsa algorithm is one of the earliest examples of quantum algorithms showing significant advantages over classical methods. It uses only one query to determine whether a given function is constant or in equilibrium. In normal computing, determining whether a function is constant or in equilibrium usually requires multiple evaluations, and in the worst case, more than half of the inputs. However, quantum methods use superposition and quantum interference to answer the questions we want with only one evaluation. After using Quizzkey and running it on the IBM Quantum Experience platform, I can also more intuitively understand the efficiency and future potential of quantum algorithms. Thanks for watching my video.